Hi, today on Viva Bites we're going to talk about mechanosensory feedback from little structures called Campaniform sensilla on wings specifically. So why is this of interest? During flapping flights, insect wings deform, which causes strain, and this strain can be sensed by little structures called Campaniform sensilla. Now in the wings, the Campaniform sensilla provide neural feedback, which is thought to be partly responsible for coordinating the left and right wings when it's flapping, and fine-tunes wing motions via activating the flight steering muscle. So I did a short video on that, and one of the first people to sort of look into this was perhaps Pringle, who studied cockroach tibia, specifically the Campaniform on the cockroach tibia. So where are the sensilla located? So they're found in strategic and very stereotypical locations on the wings, but also other appendages such as the halteres in Diptera and legs, and you can find them as either single Campaniform sensilla, so one at a time, or you can find them in field, so a sort of cluster of different sensilla. So the wild type wing blade has the following typical distribution. On the dorsal surface you'll find what are called the rad fields, so the radial fields A through E, so A, B, C is on the proximal radius. D and E are on the more medial part of the radial veins. And on the distal radius you then have two Campaniform sensilla, one called the dorsal humeral cross-vein sensillum, abbreviated as D.HCV, and the giant sensillum of the radius, probably because it's very big, and then you've got two Campaniform sensilla on the first longitudinal vein near the tip of the costa, the proximal and distal twin sensilla of the margin. That's roughly where the break is if you look at a Drosophila melanogaster wing along the leading edge. And then you've got the anterior cross-vein Campaniform sensillum. And finally, you have usually three, but occasionally four, or even it's been reported up to five Campaniform sensilla on the third longitudinal vein. And they're abbreviated as L3-1, and then L3-2 and L3-3, obviously. On the ventral surface, you also have the rad fields, so the ventral rad A to ventral rad C fields. There don't seem to be any corresponding radial D and E fields on the ventral surface. And you have the ventral humeral crossvein. You also have one Campaniform sensillum on the third longitudinal vein, abbreviated as V.L3. So now that we've seen where they are, what exactly does this thing look like? So a stereotypical sensillum is formed of a socket, a cuticular socket around a sort of bell-shaped structure, and to that structure, to this cap as it's called, you'll have a sensory dendrite, which forms a bit of a fan and attaches to it, to the hypodermal elements, and then that branches down into a primary bipolar sensory neuron, which relays the input to the central nervous system, and in particular to the flight steering muscles. So this message is sent when the Campaniform sensilla deforms under strains, which cause the cap to become indented. How are they categorized? So different Campaniform sensilla have very slight modifications on this very stereotypical description. So, and in particular, you've got changes in morphology, in the neuron position within the central nervous system, and also the electrical activity is different. So let's start with the morphological subtleties. There are different types of sensilla which can be categorized based on whether they've got a circular or an elliptical outline, a high or low profile. That's sort of how much out of the skin of the cuticle they're found. And finally, whether they've got an actual socket or not around the cap. And Cole and Palker define 6 classes based on those 3 categories, so you can go and see for more detail, and they've got illustrations. They also sort of classify a separate another type of sensillum as a separate class, and they call it the large Campaniform sensillum. Just as a side note, why is it important whether they're elliptical or not? Well, ellipticity has been shown to provide directional sensitivity, in particular along the short axis of the ellipse. So that will cause that will cause the Campaniform to fire when there are strains in certain directions but not in others. Now coming on, what is the large Campaniform sensilla, which is probably the most important to us if we're looking at the rest of the wing. Palker et al. 1979 describes the large Campaniform sensillum as being singly innervated and forming particularly large axons. So really they're kind of quite big, a lot bigger than the 6 categories that Cole and Palker classified. And there seems to be a bit of a consensus as to what the Campaniform sensilla, which ones are included in the large category. So these include the giant sensillum of the radius, the proximal and the distal twin sensilla of the margin, the L3, 1, 2 and 3, sort of on the dorsal side, the anterior crossvein sensillum, and the ventral L3 Campaniform sensillum. It's less clear about the humeral crossvein, both dorsal and ventral, so that's a bit of another debate really. And they also seem to have quite characteristic sizes. So in particular, the large Campaniform tend to be about 10 micrometers in diameter. So now that you've classified them according to morphology, you can also classify them according to the location of the neuron within the central nervous system. So whether it is dorsal or ventral. So the small Campaniform sensilla, which corresponds to the 6 classes that Cole and Palker described, they enter through the wing hinge, and then they go dorsally into the thorax, which is unusual because normally ventral insects have a ventral track, not a dorsal one. So that's for the small sensilla. The large Campaniform sensilla follow the ventral tract, but they can also be differentiated further into 2 subcategories if you want. So the axons follow either the lateral or the medial ventral tract. So lateral is really to the side. If you sort of imagine looking top down onto a fly, and you'll see it's sort of like to the right or to the left, but not in the middle. Whereas the medial tract is pretty much smack in the middle. And this really correlates quite strongly with the time of birth of the neuron. And finally, I mentioned the electrical output changes between Campaniform sensilla. So you can classify them according to Dickinson and Palker when exposed to the same stimulus as being either rapid adapting or slow adapting. What this means is that under a constant strain, the rapid adapting campaniform fire one big spike and then stop because they've become neurally adapted, whereas the slow adapting campaniform continuously fire for the whole duration of the stimulus. In addition to having different spike characteristics under constant strains, the Campaniform sensilla are sensitive to the rate of strain deformation. So in the case of rapid deformation, such as, for instance, high frequency flapping, both will fire, both rapid and slow adapting sensilla will fire. On the other hand, if the wing is deformed slowly, for example, if the fly is grooming its wings, then only the slow adapting Campaniform sensilla will fire. There's a direct relationship, really, between the time of birth of the neuron, the electrophysiology in which tract in the central nervous system is followed. The rapid and slow adapting correspond to sensilla with the medial or early differentiating and the laterally and late differentiating neurons respectively. So the sensilla that differentiate early, follow medial tract and are rapid adapting are the distal twin sensillum of the margin, the giant sensillum of the radius, the anterior cross vein sensillum, and the L3-2 dorsal sensillum. The Campaniform sensilla which differentiate later, follow a lateral tract and are slow adapting are the proximal twin sensillum of the margin, the ventral L3 sensillum, the dorsal L3-1 and L3-3 sensilla. The dorsal and ventral humeral cross veins are exceptions and a bit of a subject of debate in terms of all three, really, morphology, neuron position and electrical output, but I won't go into those really. Now, how do the Campaniform sensilla impact flight? Well, in another video I sort of went into the different types of muscle that are present in flies. So you've got the flight power muscles, the asynchronous that drive the wings to beat, and you've got the wing kinematics, which are fine-tuned by a set of steering muscles and sclerites, and in particular the B1, the first basilar muscle. So yeah, the wing Campaniform sensilla are thought to provide feedback to the various steering muscles, and particularly entrain the B1 motor neuron. As a wing undergoes, as a wing in flight flaps, it undergoes a torsion wave from tip to hinge. If you want to know more about that, read up on ENOS 1988 and 1989. And as this wave progresses, you see a single spike per cycle is elicited from the rapid Campaniform sensilla, and with increasing amplitude of the wave, you've got an increasing number of sensilla that are recruited. And the cumulative feedback and relative time delays between the action potentials from the different Campaniform sensilla is thought to encode accurately how the wing deforms. Shouldn't forget as well that there is also bending along the chord and the span, and this is likely to also impact how the sensilla, how and when they fire. Thank you very much.